everyone, my name is Victor and I'm a developer advocate for ClearML. I was working on a blog post, so this is actually an unplanned video, but I couldn't help sharing it with you. ClearML is the ultimate benchmarking tool. So the blog post was about benchmarking some machine learning models on different architectures of GPUs, but the point is that in general, if you want to test anything on multiple machines, ClearML is going to be the ultimate pick. And actually, I made a little diagram to explain why and how, and then also prepared some code so that I can show you. For those who don't know, ClearML is an MLOps company. It's basically meant to be a toolkit full of modules that data scientists and machine learning engineers can use to better deploy and train their models. Now, today, we're only going to use two modules of that, which is the experiment manager, which will keep track of all of our experiments, and then the orchestration module, which will actually run those experiments on the remote machines that we want to benchmark. So let's get started. So this is my diagram. It's just very quickly thrown together, so I'm sorry about that, but I hope it will make the picture a little bit clearer. So we'll actually start on our local machine, and we have some Python code there that we actually want to run. Now, what exactly we want to run doesn't really matter in this video. You should check out the blog post if you want to know more. We'll be running YOLOv8, but in general, this can be any workload. Any workload that you're interested in can be run using ClearML. So what we'll do first is we'll run this experiment, I'll call it experiment, and we'll run this on our local machine first, right? So this is just a bunch of code in a Python virtual environment that can be run on your machine. And so what will happen is ClearML will capture this and will create a new experiment in the experiment manager. The experiment manager looks a bit like this. So it's currently empty. Let me zoom it in a little bit for you. So it looks like this. It's just a list of experiments, and every time you run your code, a new entry gets added into this list. And then if you click on details here, you'll see that you have the source code, any uncommitted changes, your configuration options, any models that were trained, plots like confusion matrices, scalars, etc., right? So this is all for later, but just so you know what this experiment entails, this is all that I'm talking about. So all of these plots and config options, etc. So once this experiment is in the experiment manager, what ClearML allows you to do, and I'll show you in the code later on what exactly that means, but you can actually clone this experiment. So I'll call this, clone of our experiment. I think I said experiment. For now, it's an experiment. So I said clone of experiment or experiments, and now we have a clone in the experiment manager. And what this allows us to do is change some of the parameters. And like, for example, we can set a higher batch size. We can set it to train on a different data set. It's very, very useful stuff. But in our case, what will be the most interesting is we can take this experiment now, and then we can add it to a bunch of queues. And this is where these queues come in, right? So we have 6 of these queues, and queues are literally just what they sound. They're like a queue of tasks that will be executed one after the other, right? So you can make specific queues, add as many as you want with specific names. And because we're going to be using the autoscalers later, and I'll explain you what those are in just a minute, I want to make a queue for every machine that I want to run the benchmark on. So for example, here, I want to run the benchmark on a machine with a 3060 Ti GPU, one with a 3080, one with a 3090, and then some similar machines on AWS as well. So I'm going to be making all of these queues, and then we can take the clone of our experiment and then clone it several times again, and then add it into each of these queues, right? Because that's the kind of job that we want to execute in each of these machines as part of our benchmark. Now, what does the autoscaler do, and why are we enqueuing everything? So the autoscaler in ClearML is actually a service that runs in the background and that is continuously listening to specific queues. So I set up, for example, the Genesis autoscaler, which is from Genesis Cloud. You also have an AWS autoscaler for AWS, you have a GCP autoscaler, etc., etc. So specifically here, I want to be focusing on Genesis and AWS by using these autoscalers. And these autoscalers are then assigned to specific queues. In this case, this autoscaler will listen to the 3060 Ti queue, to the 3080 Ti queue, and 3090 Ti queue, and it will take these experiments. So once there is an experiment in that queue, it will actually spin up new machines, and I've put them here. There we go. They will both spin up new machines in their respective clouds, right? Because they're listening for tasks to be executed. So then the autoscaler spins up the right machines, and then it knows, okay, every task that is in the 3060 Ti queue, I'll assign it to the 3060 Ti VM that I've just set up. Then the same with our 3080. Let me take it like this. And then the same with our 3090. So it will take these experiments, schedule them for you automatically on these VMs. And then these are experiments, just like any other. So these will actually end up sending all of their data back to the experiment manager, right? And so in the experiment manager, we now have an incredibly useful benchmarking tool and overview tool, because we can just keep track of what is happening. How are the experiments performing? How fast are they? On which machines were they run? You can compare them. We'll see all of that in just a second. Obviously, the AWS Autoscaler is going to be doing the same thing. So here, it's also scheduling these. Now, a cool fun fact is that once these tasks are executed, these autoscalers will actually spin those VMs back down again as well. So we actually just paid only the cloud providers for the very little amount of time that it took to actually train the model, and then it shuts down the machines again and you stop paying. So how awesome is that in terms of tooling for your benchmarking? Now let's see what that actually looks like in real life. Okay, so the first thing that I want to show you is this local experiment, right? So let me go to my code here. This is what I've set up. Now, all of this code will be available. I'll add a link down in the description. But in this case, it's relatively simple. So basically, I initialize ClearML, give it some name and etc. Then set some base Docker configurations so that we can actually later run it remotely relatively easily. For example, you needed to install curl so we can actually get the data set. It's relatively simple stuff. Then I create a dictionary with all of the arguments or the variables, the hyperparameters that I want to give to YOLOv8 to be able to train correctly, and we'll be able to override these later on when we clone our experiments. We task.connect it to the ClearML task, and then we choose the model variant, also set that parameter so we can change that as well later if we wanted to. Then we create our YOLO and we train it as well. So this is very, very simple stuff. If I run this locally, it will take a little time because YOLOv8 is really nice to train, but I did take like a relatively big data set. So it will take a little time to train, but you can see here that it's creating a new task in the experiment manager. So this task, and currently YOLOv8 has started to work. So this is on my local machine that this is currently running. I've just run this. So this is what we just have done. We've created our experiment into our local machine, and ClearML has detected it and has sent it to the experiment manager. If we look at our experiment manager, let me go here, we see YOLOv8 video, which is the project name that we chose here. We click on it and we can see that it's currently running. So we have all of our information right here. We have our configurations, we have the console logs as they are coming in right from here. We have the scalars, which will come in later, and we have plots at the end, etc., etc. You get the gist. So what I want to do now is clone these, right? We want to create a clone of this experiment so that we can put it in all of those queues. So if I go back here, I don't even have to wait for the experiment to finish running. I can just clone it, because what the most important part here is this, like the execution information. So for example, the source code, where did I get the code from? Any uncommitted changes, any installed packages and containers, all of this stuff is what ClearML uses to then set up the remote machines so that it can run the exact same code. So I can right click on this, click clone, I will call it clone of template task. And then now, remember what I want to do here. So I have the clone of my experiment. Now I want to enqueue this into each of my queues, right? Now, if I go to my workers and queues here and go over to the queues tab, you'll see that I have already created all of these queues. I have my 3060 Ti, I have my 3080, I have all of these Amazon machines. You can always create new ones right here with new queue. You can make as many as you want with as many names as you want. So let's go back to our template task here. Our clone let's just first go into the configuration and edit it some, right? Because my local machine isn't that very powerful, but I'm pretty sure that a 3090 should be able to do better. So I can, for example, change it to 8 batch size. I can clean up, for example, here. I know that there are some paths here to my local machine, so we want to get rid of those, that it doesn't, yeah, have a problem with that. And then I can also do this, for example, and then save it, right? So we changed some of these configuration parameters for the remote machine to run. Now we can enqueue this, or we can take some multiple clones of that and clone of clone, etc., etc. And then we can enqueue these. For example, here I want this into the 3080, and I want this one into the 3090 queue. Now it might be I put the batch size to 8, it might be that it's a bit much for the 3080, but then it'll just fail, and I'll be able to see why it failed in the console logs. You'll get an out-of-memory error right there. Currently, these are running, so what we have in our diagram here is we have just sent all of our clones, or I've just sent this clone to one of my queues, or both of my queues, right? Now, this is very cool and awesome, but it's also very manual work. So that's not what I want to do. I want to show you how you can do this automatically, fully automatically with the Python SDK, which is even handier than this, and you'll be able to launch all of your tasks right at the same time. I tell you, it's really awesome. I've been loving this workflow. Right, so if I jump over here, I'll let this train. I don't actually mind that much, but I want to show you here. So benchmarking YOLOv8 on everything using ClearML. So what I want to do here, in order to do the same workflow, like clone everything and then send it to the respective queues, is I want to get my template task, right? So the first task that I made right here, I want to actually get that and clone it several times. So let me, let me take the clone here, right? We changed the parameters there, so we actually want to take that one. I'll copy the ID right here, add it here, and now we have our template task. Let me show you. Template task. Oh, I caps locked it. Dot name is clone of template task, right? So this is the exact task that we were talking about. Now it's as simple as just setting up a list of queues that we want to enqueue this into. So here, these are all the ones that I want to benchmark for my blog post. So this is the ones that I chose. You can choose whatever you want, obviously. I've also already set up the autoscalers. These will basically be monitoring these queues for any incoming tasks so that it can actually spin up machines. I'll actually show that to you. So you have the ClearML CPU compute, or GPU compute, which is based on Genesis Cloud, 100% green energy, by the way, which is awesome. And you can see here we have autoscalers running for 3080, 3090. The 3080 is currently running. It's running on a task because we've enqueued our previous task. Actually, let me show you. So this one is currently running, and if I'm not mistaken, it should be running here on a, oh no, it's the clone, sorry. This one is currently running on this worker, and this worker is our GPU worker. So it's the one from here, which is why this one is currently on 1. Then we have the 3080 and 3090 memory optimized. So the 3080 and the 3090 are currently on 1 because that's where we've actually put tasks in the queue just right before, right? Right, the AWS autoscaler also looks awesome because now here is this awesome dashboard of what are all the machines that are currently running, right? And you'll see these pop up to 1. We have 1 idle instance because I ran a task before on the G5, and it's currently waiting until there is a timeout limit where it will be spun back down again. Excellent. So if we go back here, these are the queues that we want to run everything in. So let me execute that cell. I set up the ideal batch size for each of them. I'll give you a hint on how to do that later on, but it's relatively easy. We'll gloss over it for now. And then we have the cost mapping as well, because obviously in the blog post, I want to show what everything costs and how efficient it is as well. Right, and then there are some helper functions that I won't go deeper into. This is basically, you'll see at the moment. At the moment, I'll use them. Now, I want to enqueue all the things, right? So this is where actually the enqueuing comes in. So now I want a list of tasks, and then for each queue in the queues, which corresponds to each machine that I want to run everything on, I want to clone and enqueue my template task into this new queue with a number of epochs that I define, with a batch size that is ideal for that specific queue, with a new tag so that I can keep track of it. This is just for organization purposes. And I want to override the normal dataset with the visdrone dataset because it's kind of bigger. Coco 128 is like the default, but it only has 128 images, which is not ideal if you want to test batch sizes. So this is a little bigger for that reason. And I'm also enqueuing one with the ideal batch size of a lower power of 2, which basically serves as a backup. If this one goes out of memory, I always have this one as well. Now, if I run this, so I'll actually show you first clone and enqueue. This basically creates a new task by cloning the source task, then updates the parameters for the epochs, for the batch size, adds the tags, and updates the parameters for the dataset, can rename it to specifically which machine is running it, and then enqueue it in the queue. So this is fairly simple, and this is doing all of the heavy lifting of the blog post, right? Of the benchmarking that we want to be doing. Now, currently it's all enqueuing these tasks. So what should happen is if we go here to our list here, our experiment list, what you'll see is that there's tasks pouring in with the visdrone label that are in draft mode, or either pending or draft mode. So draft mode is while it's still working, and then here they're all pending. So these are currently being added to the queues so that the autoscalers will detect them, spin up machines, and then run everything right in this interface. And then we'll be able to like clone compare everything, like select everything. It's super, super cool. So I always feel like I'm raising an army here. It's super fun. So what we should technically see, it might take a little while before it kicks in, but we should see these dials go up. And you can see here that the queues are being filled. We have 2 tasks for each, which is the one with the optimal batch size and one with the lower power of 2 of that same batch size. Now, this takes a lot of time, obviously. That's why it's benchmarking, but it's all automated, which is beautiful. But I can already show you what it looks like when I did it before, and I have a project here with these finished or completed benchmarking tools right there. And so this is why ClearML really shines, or where ClearML really shines. Not only can it like run all of your stuff on remote machines and like nicely consolidate all of the information in this overview, you can also then do analysis. And that's so fun. Like for example, I could take the 3080 and the 3080 optimized, which has like more CPUs and more RAM to deal with or to work with. And if we compare them, we can actually take a look here at, for example, the CPU core. So, oh yeah, this is why this one is optimized. It has double the CPU cores, it has more memory to work with, but it has the same 3080 GPU. Where is it? The 3080 GPU, there it is. So same 10 gigabytes 3080 GPU. Awesome. And now we can actually compare these two and see how well they're doing. So we have, for example, the epoch time, which in this case, obviously the optimized is actually quite a bit faster for each epoch than the normal 3080. Same here, we can compare metrics. Luckily, the MAP is very, very similar, even though the batch sizes are different. They shouldn't actually be that far apart. But we're only training for 10 epochs as well. You can have plots and compare them, like have insights from there and see what the differences are. This is so cool. Like I can't stop saying this. This is the best way to do benchmarking in my humble opinion. So just after recording this, I actually found another awesome insight that I had while comparing the 3090 with the 3090 optimized. Now, as you can see here, the 3090, the normal 3090, actually has only 4 CPU cores attached to it, while the 3090 optimized has double that. It's the same story with the RAM as well, the system memory. We have 23 gigabytes here and double that right here. So you can actually see why that gives such a big performance difference when you go to the CPU usage. Now, ClearML takes care of a lot of things for you. One of those things is it already captures things like CPU usage or RAM usage of your machine. It actually logs those as a scalar fully automatically. You don't even have to think about that. So when we click here, we can go to the CPU usage right here. And as you see, the 3090 machine with its 4 CPU cores is actually flat out. It's 99% most of the time, it's just slammed. And so the difference with the 3090 here is pretty obvious, right? You can just see it in the graph. This is bottlenecked on the CPU. So this section right here is why the 3090 isn't getting to its full potential. Now, if we then go to our epoch time here and click here, you can see that even though they have the same GPU, they still have such a huge difference in performance. And the reason is because the CPU usage is slammed, and you can see it right here in the comparison view. How cool is that? I just wanted to throw that in there. Enjoy the rest of the video. Now, the crown jewel, what do I put in my blog post, right? Crunch them results. So the idea is get the latest tasks from the YOLOv8. I'll take the ones that are completed, right, for this example. So this is going to be these tasks, all of these that are already done. I'll get all of the tasks from there, and I will basically queue or look into ClearML and get the task that is completed ordered by its batch size. So we always stake the task with the highest batch size that was correctly completed. In this way, we can make very, very sure that throughout all of our experiments, we'll always get the one that you want to be able to compare. That is basically giving it the best shot at success. Right, so we have all of these. Their task name and task ID are visible here. And then we can select the runtimes, because that's the cool thing about ClearML. All of this data is in the server now, on the experiment manager. Then we can, for example, say, I want to get the reported scalars, the epoch time, and the y-axis of that. We'll chop off the 2 and -2, which basically means if I go in here, I can go to scalars, epoch time, and you'll see that the first two are always a little bit out of whack, out of line, because it's like either stopping or starting. It's not ideal, has to be warmed up. So we'll take an average of all of the points in between as our metric, right? So if I now go back here, then you'll see for task and tasks, if it has epoch time, we'll take that epoch time and then give you that as a runtime. So this will give us the runtimes of all of the different machines and plot it nice and clear for us. So as you can see, you have the AWS machines here, you have the G5's machines that are very, very strong, especially the 2x large, which is really, really cool. And then you have the Genesis machines as well with the 3080, 3090 and the optimized ones. Now we can combine this with the pricing information. Now all of these numbers are still dummy numbers. I'm still working on the blog post. I just couldn't help myself to already make a video and show you what this is like. And then you can plot this as well, and you get a full overview of the cost in dollars per hour and the performance cost in dollars per epoch for each of these machines, right? And then you can even say, okay, I want to highlight one specific one. For example, in this case, we take the 2x large from AWS, and we compare it to our own 3090 optimized machine, which has more or less the same cost in dollars per hour, which is 83.8 or 84, which is basically the same. But then the performance cost in dollars per epoch is much, much lower in the ClearML 3090 example, which is quite a significant difference, right? So this is why ClearML is so cool to deal with in terms of benchmarking, because you can make plots like this. One last thing that I want to show you is getting the right batch size. Because ClearML keeps track of all of these parameters and all of these scalars and all of these metrics, one thing that ClearML automatically keeps track of for you is the GPU usage. So this is monitored GPU. You have the GPU memory usage, you have the utilization as well. And then you can go in and ask it to report the maximum GPU memory usage for every task. And then you can see, okay, it's all 97, 97, 90, 98, 92, 91. It's all very, very high, so that we're pretty sure that we're dealing with the correct optimized batch size here, and that we give each of these machines its best shot at success. Right, so this is basically the overview. I hope you found this interesting. I hope you will use ClearML more in the future for benchmarking. You can use anything as the workload. It doesn't have to be machine learning or deep learning. You can just throw anything in there, have it run, and then have a complete, clear overview of all of the things that you run, and you can compare them, and you can generate graphs and stats and whatnot, and create cool blog posts along the way. So I hope you found this interesting again. And thank you for watching. See you next time. Bye-bye.